In this next chapter, we are going to discuss probability. So we'll first start with random circumstances. So statistics is a collection of procedures and principles for gathering data and analyzing information to help us make decisions when faced with uncertainty. We use probabilities to talk about events that are uncertain. Now, a random circumstance is a circumstance in which the outcome is unpredictable and the outcome is not determined until it is observed. So things like rolling a coin, having a child, rolling a dice, those are all random circumstances. A probability, and maybe you already know this, is a number between 0 and 1 that's assigned to a possible outcome of a random circumstance. A probability of 0 means an event is impossible or never happens, and a probability of 1 means an event always happens. So, for example, an impossible event would be that you roll a 7 on a normal 6-sided die. As in, that's not possible. There is no 7, so you can't do it. The probability of that event happening is 0. An event that always happens, or a guaranteed event, would be that you roll a 1, 2, 3, 4, 5, or 6. As in any one of those, well, the probability of that happening is 1. So here's an example of a random circumstance. According to a U.S. Department of Transportation website, 78.7% of domestic flights flown by the top 18 U.S. airlines in January 2010 arrived on time. Represent this in terms of a random circumstance and associated probability. So first, the random circumstance. So the random circumstance here is on-time arrival of a flight. And the probability will say P of on time. So the P means we're finding the probability, and the on time inside the parentheses tells us we're finding the probability of. Well, that would be 78.7 out of 100. That's what a percent is, or 0.787. Remember that our probabilities are between 0 and 1. Give an example of a random circumstance in which the outcome is not determined until we observe it. So in this case, we don't know what's going to happen until we actually see it happen, as opposed to a situation where you don't know what's going to happen, but it's already been decided, even though you just haven't seen it yet. And that's the next example. So for this one, an example of a random circumstance in which the outcome isn't determined until you observe it could be whether a lottery ticket is a winner as the numbers are being drawn. An example where the outcome is already determined, but our knowledge of it is uncertain, could be something like a scratch-off ticket. As in whether this is a winner, whether or not because if it's a winner, it's already been determined. Another example could be the gender of a baby. When you're figuring out the gender of a baby, it's already been determined. It's just a random, you just don't know what it is. So your knowledge of it is uncertain. So is each of the following values a legitimate probability? Explain. Remember that probabilities are between 0 and 1. So is 0.82 between 0 and 1? Yes, this is a valid probability. Is 0 a valid probability? Yes, it's totally fine to include 0. 1.5 is not. It's too big. Negative 0.3 is also not, and that's because it's negative. So that should be pretty easy. There are different interpretations of probability, but one is called the relative frequency interpretation of probability. This applies to situations in which you can envision repeatedly observing the results of a random circumstance, and the probability is then the proportion of times an event would occur over the long run. So, relative frequency interpretation. So, for example, you could observe the gender of births over the long run. And then the probability of having a girl would equal the number of girls you observed over the total number of births. And if this comes out to be close to 1/2, you know the assumption that each gender is equally likely is a valid one. So suppose that you live in a city that has 125,000 households, and a polling agency selects 1,000 of them to contact for a survey. Express this fact as a proportion, a percent, and a probability. So the proportion of households selected, 1,000 out of 125,000, which when we reduce that to lowest terms, just canceling those zeros, we get 1 over 125. I'm actually going to do probability next. The probability is 1 over 125, which as a decimal is 0.008. And then the percent is quite easy. The percent of households selected, remember the decimal moves over 2 spots, is 0.8%. So how to determine the relative frequency probability of an outcome? Method 1 is you can just make an assumption about the physical world and then use that assumption to assign your probability. So, for example, we assume a coin is fair. And then we say the probability of heads is equal to 0.5. And probability of tails is also equal to 0.5 on one individual flip. You also could say you assume births are equally likely, and the probability of having a boy is 0.5, girl is 0.5. Method 2 would be to actually observe the relative frequency over a long time. So what this means is you observe frequency over many, many repetitions. So, for example, I could find the probability of passing Stat 200 in this way. I could compute the number of students who passed over the number of total students. And the longer I observe this, the more likely I will get this probability to sort of stabilize and be close to what the true probability of passing Stat 200 is. Now we need some terminology to talk about probabilities. So the first thing is called a simple event. A simple event is a unique possible outcome of a random circumstance. Okay, and I think it will be helpful to have examples. So up here, let's suppose we roll a 6-sided die. An example of a simple event would be to roll a 1. That's a simple event. Or roll a 2, or roll a 3. But the simple event just contains that one thing, not more than one. The collection of all possible simple events, that is called the sample space. We're going to usually abbreviate that with the letter capital S. And for the example of rolling a die, S is equal to just all the possible rolls. You could roll a 1, you could roll a 2, you could roll a 3, you could roll a 4, you could roll a 5, or you could roll a 6. And every single event, the 1, the 2, the 3, the 4, the 5, the 6, are simple events. An event that includes 2 or more simple events, that's called a compound event. And usually we represent these with different letters of some sort. So we'll say like the event A could be that you roll a 1 or a 2. And that contains the 2 simple events, 1 and 2. An event is just a collection of 1 or more simple events in the sample space. So that's just pretty much another way of saying compound event. Now this we've already discussed a little bit, but it doesn't hurt to review it. So each probability, to be a valid probability, must be between what 2 numbers? So 0 and 1. And it's okay for them a probability to be 0 and 1. Another way to write that would be 0 less than or equal to p less than or equal to 1. And if you sum over probabilities over all simple events, the total is always going to be 1, because you've accounted for everything that could happen. So think about, back to the die example, the probability of 1 plus probability of 2 all the way up to probability of rolling a 6. Well, each of those would be a 6th, a 6th, a 3 would have a probability of 6, 4 would have a probability of 6, 5 1/6, and 7 1/6, which makes 6 6 or 1. If there are k equally likely simple events in the sample space, then the probability is 1 over k for each event. So for example, if you roll a die and you record the number that appears, there are 6 simple events, and each has probability 1/6. Or if we were talking about choosing a random letter from the alphabet, there would be 26 different simple events, and each has probability 1/26. Now, when you're looking for probabilities, the basic starting point should be this. The first thing you should do is determine the number of events in your sample space. And we'll have some counting arguments to do that. And then the next thing is to determine the number of events that meet your given criteria, or the number of different things that are inside the event you want to talk about. So, for example, suppose that a lottery number is a 3-digit number between 000 and 999. What is the probability that the last digit is a 9? So first of all, let's talk about the total number of events in the sample space. In S. Well, first, it's pretty easy to observe that the number of numbers between 000 and 999 actually is 1,000. The reason it's 1,000 and not 999 is because 000 also counts. Another way to think about that is that you're choosing 3 numbers and you have 1, 2, 3 places to fill in. And you have 10 choices for your first number, which 0 through 9, 10 for your second number, 0 through 9, and 10 for your last, 0 through 9. And you multiply those, and that gives you 10 to the third, or 1,000. That general principle applies for counting up how many things are in something like this sample space. And if these had been letters, this would have been 26 times 26 times 26. Okay. All right, then let's talk about the number of events where the last digit is a 9. Number of events that end with 9 at the end. Okay, so once again, we have 3 numbers to choose. The first number can be any of those 10 possibilities. The next number can be any of those 10, and the last number has to be a 9. So for that spot, we only have one choice. This is 10 squared or 100. And just to make it easier, let's call that last digit a 9. Let's call that, just give it a letter, call it A. Then the probability of A occurring is 100 over 1,000, which reduces to 1/10 or 0.1. Okay, how about all 3 digits being the same? So the number of events here didn't change. Let's talk about how to do this one the counting way, and then let's talk about how to do it just by listing. So, number of events with all the same. 2, 3. Okay. For your first number, you can pick any one of 10 things. But the tricky thing here is that once you've chosen that number, like once you've picked it and it's a 5, then you have to pick a 5 and a 5 again, which means there's only one choice for your next number and one for the last number, for a total of 10 events. So picking this fixes that. And that is legitimately a little bit tricky, but you can verify it by just listing out all of the things who have 3 digits the same. They are 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5. I think you get the idea. Up to 9, 9, 9. And if you count, there are 10 of those. So this event is small enough that you can actually list those out, but it's also useful to have this kind of thinking going for you a teensy bit. And let's call this event B. The probability of event B is 10 out of 1,000, which reduces to 1 out of 100, or 0.01. We have some other vocabulary definitions. Two events are called complementary. If they do not contain any of the same simple events, and together they cover the whole sample space. For an event A, the notation for the complement is A with a little superscript of C. And also, as they cover the sample space, the probability of A plus probability of A complement has to be equal to 1. Now here's a Venn diagram to kind of explain what I mean. So suppose that this box contains all of our simple events, our sample space S. So S is the box. Suppose that this is the event A. Like all the events that are in A live inside that bubble. This stuff outside of A, that's a complement. So together, those two things make up the entire sample space. And then, as a result, P of A plus P of A complement is going to have to be 1, because that covers all the simple events, and the probability of all simple events is 1. Okay, what is the probability that you will win the lottery discussed in example 5? Okay, so the probability that you will win means you have to match all 3 numbers. So we're assuming that there's just one winning ticket out of 1,000 total tickets, which is 0.001. That wasn't so hard to figure out. Now, not win. You observe that this is the complement of winning. So the probability of not winning plus the probability of winning has to equal 0.001 or has to equal 1, because those two events are complements. Okay, we don't know P of not win, but we do know P of win is 1 over 1,000. And we can solve for this guy by taking the 1 over 1,000 away from both sides. So the probability of not winning is 1 minus 1 over 1,000, or 999 over 1,000. So two events are complementary if they have nothing in common, and together they cover the whole sample space. But there are lots of events that have nothing in common and just don't cover the sample space. And that is something called being mutually exclusive. So two events are called mutually exclusive events if they do not contain any of the same simple events, but they don't have to cover the entire sample space. So back to our little Venn diagram picture, if the box is my sample space, here's my event A, here's my event B. A and B don't have any overlap, but they don't cover the whole sample space. So suppose you roll a 6-sided die. Give examples of events that are complementary and mutually exclusive. Okay, so complementary could be the event A, you roll an even, and B, you roll an odd. That's one example of complementary events. Another example, the event A could be that you roll a 1, and the event B could be you roll any other number, 2, 3, 4, 5, or 6. Okay, mutually exclusive, the event A could be that you roll a 1 or a 2, and B could be the event that you roll a 3 or 4. And those have no simple events in common, but they don't cover the whole sample space. it would be okay if they did cover the whole sample space, as in, this says they do not need to cover the entire sample space, but it's okay if they do. It just means that they're then complementary events also. Another event A could be that you roll an even, as in a 2, 4, or 6. And B could be the event that you roll just a simple event of rolling a 1. Those are also mutually exclusive. So suppose you have a 3-digit lottery, as described in example 5. Are the events A, all digits are the same, and the events B, the first and last digits are different, complementary? Okay, all the digits are the same, and the first and last digits are different. So does this cover all possible events? Okay, well, if the first and last digits have to be different, things like 919 would be not included. Not included in A because the digits aren't all the same, and not included in B because the first and last digits are different. So in this case, we know no, they're not complementary. They do not cover the sample space. And that's because we found an example of an event that wasn't in either of them. Are they mutually exclusive? So the question you ask yourself there is, can an event be in both? If yes, then they're not mutually exclusive. If no, then they are mutually exclusive. Okay, so can an event be in A and B? Can an event have all 3 digits being the same and the first and last digits being different? So no, that means A and B have no overlap. So yes, they are mutually exclusive. Another important kind of event is an independent and dependent event. So 2 events are called independent of each other if knowing one will occur does not change the probability of the other. So, for example, flipping a coin and drawing a card. Those are independent events. Or the gender of a baby on a given birth is independent from the gender that came before. 2 events are dependent if knowing one event will occur will change the outcome of the other. So, for example, drawing 2 cards from a deck. Once you draw the first card, the probability of what the second card will be changes depending on what the first card was. Now, this intuitive definition is legitimately a little bit tricky, and really a better way to check it is with the formula that we're going to learn a few lessons from now. So for now, just try to muddle your way through with the intuitive definition, and then we will learn a better way to check in a later lesson once we know a little bit more about probability. So suppose you draw 2 cards from a deck. When are these events independent and when are they dependent? So these events will be independent if the first card is put back. And the deck is mixed. In that case, what you drew on the first go doesn't affect what you get on the next go, but they will be dependent if you do not put the card back. So for example, if you draw the Queen of Hearts on the first go, then the probability of drawing the Queen of Spades changes relative to what it would have been before that Queen of Hearts was taken out, because you have fewer things in the deck. Okay, remember that the event A complement is the complement of the event A. Are these events mutually exclusive? Remember, the only requirement for mutually exclusive is that they contain none of the same simple events. And if that's true, these events are mutually exclusive. So the answer here is yes. A and A complement do not have any events in common. Okay, are A and A complement independent? In other words, if A occurs, does P of A complement change? And once you know A occurs, P of A complement has to be 0. So once A happens, A complement can't happen. And so the fact that this is forced to be 0 means that that probability is changed somehow. So these events are not independent. We will have a better way to check in a later lesson. So for now, just deal with it as you can, and we will have a better way to check in section 7.4. All right, here we're going to look at sort of a relative frequency interpretation probability. So it's really commonly known among people who study stuff like this that people are really, really bad at picking random numbers. So in this example, 190 students were asked to pick a number from 1 to 10, and the number of students selecting each number were as follows. And you can see that students did not pick each number with like sort of equal frequency. 7 was way more likely to be chosen than 1. Only 2 people chose the number 1. And so 7 is particularly overrepresented. And it's sort of an interesting story, but this is actually one way that people use to check if elections have been forged or rigged. They look and see, I think it must be people's birthdays or some other sort of identification when they register to vote, and if the numbers that appear to not be randomly distributed, it seems like somebody has maybe cheated and filled those numbers in. So there are examples of that being used as evidence that an election was fraudulent. Okay, so suppose that a student is asked to choose a number between 1 and 10. Let's let A be the event that the student chooses a 5, and B be the event that the student chooses an even number. So A contains the event just 5, and B contains these simple events 2, 4, 6, 8, or 10. So just keep that in mind. What is the approximate probability that someone asked to pick a number from 1 to 10 will pick an odd number? So the probability of picking an odd, well, 2 people chose 1, 22 chose 3, 18 chose 5, 56 chose 7, and 14 chose 9. Out of the total number of people choosing, which is 190. Now, when you put this in a calculator, make sure that you put parentheses around this. Otherwise, it's only going to divide the 14 by the 190, not all of it. So this works out to be 0.589. You really should pause me and make sure you can make your calculator give you the same value. So it looks like picking an odd number is a little bit more likely than picking an even number based on this data. What is the probability of A and B? How about P of A or B? Okay, so P of A and B. That's the probability of being a 5 and an even number. Could someone have chosen a 5 and an even number? Okay, 5 is not an even number, guys. So the answer is no. So that probability is 0. Another way to say that is that A and B are mutually exclusive events. They contain no simple events in common. But A or B, that's the chances of picking a 5 or an even number, which kind of means you win if you pick 5 or if you pick even. So there are people that chose 5 or 18, plus all of the evens. So let's do the evens in a different color just to drive it home. 9 people chose a 2, 21 chose 4, 23 chose 6, 19 chose 8, and 6 chose 10. And that's all over 190. And same as before, parentheses here. This works out to be 0.505 approximately. Are the events A and B independent? Explain how you know. Okay, so once we know A occurs, as in you choose a 5, what does P of B become? So once you know you've chosen a 5, this forces P of B to equal 0. Because you've chosen a 5, and then there's no way that P of B can happen. So because this probability is changed, knowing A, these events are not independent. Are the events mutually exclusive? Remember, events are mutually exclusive if there is no overlap. So if you look at A and B, is there any overlap? And the answer is no. So since there's no overlap, they're mutually exclusive. So yes, there is no overlap in the events in A and B. And having no overlap means that these events are mutually exclusive. And one last example. So Alicia's statistics class meets 50 times during the semester, and each time it meets, the probability that she will be called on to answer the first question is 1 out of 50. Does this mean that she will be called on to answer the first question exactly once during the semester? And the answer is no, it doesn't. What this really tells you is that in the long run, if this class had many meetings, the proportion of times she'd be selected would be 1 out of 50. So in the long run, this class had many meetings. The proportion of times she will be called on is 1 out of 50. But it's possible she may be called on more than once or not at all in this class.